you guys have heard about DCMHS, that's Modular Hardware System, that is based on DC-SCM, Data Center Ready Secure Control Module. Today, as part of this conversation, we're going to dream what a next version of DC-SCM in the future might be, how small it could be, how feature-rich it could be. I'm Siamak Tavallaei. I'm involved with the OCP server project. I serve as an incubation committee lead for server project. And with me, we have Jean-Marie and Tim. Please.
Tim Lambert from Dell. I worked on DC-SCM 2.0, the interfaces. I'm not a mechanical guy, but help support the spec in general, as well as on the DCMHS, a lot of the HPM. Trying to figure out how to commoditize into the design spec a lot of these miscellaneous types of interfaces and things. So, we have this horizontal form factor. There's 2 verticals about to come out as 2.1, and we are looking at many flavors, internal only flavors, ways to extend from it. There's different system architectures coming that give you different internal capabilities as well as external capabilities with different sub-modules and mezzes and that kind of thing. So I think that's the context of why I'm here.
Hi, my name is Jean-Marie Verdun. I do work at HPE within the Advanced Engineering Development Group, where I'm mainly focused on management software, porting OpenBMC to HPE infrastructures. You might be well familiar about the fact that we do not have yet a DC-SCM modules at scale within HPE servers, but that is something we are working on, and we are expecting to have proof of concept of DC-SCM 2.0 modules based on HPE ASICs by the end of the year, and we will be starting some kind of bring up during the first quarter of 2023. With hopefully some kind of prototypes that we could display during our next regional OCP event, I think in Prague, in April timeframe. And we are engaging more and more within DC-SCM specification due to the fact that this is definitely something we want to adopt at scale, especially with the expansion of DCMHS.
So we've been working together for a while on initial definition of DC-SCM. We've had ideas of what it should be, and we did whatever we needed to do to make it useful for system providers, system suppliers, and for customers to do based on the discrete components we had. Now we can hopefully dream big and see if we can integrate some of those. Jean-Marie, you have also another session coming up this afternoon.
Yeah, I do have a session more specific on HPE hardware because we are still designing the BMC ASICs, so we do not use third-party ASICs. And I'll be disclosing the main characteristics of our current ASIC design, what we are doing to support it under Linux, and what is the impact with DC-SCM and the challenges that we face when we build up a proof of concept. Because we designed the ASIC before the DC-SCM specification even exists, and we need to adapt. And I think we might be providing some great feedback about some kind of limitation that we faced while building our first DC-SCM modules.
And Tim has been very much involved in definition of DC-SCM from the beginning of the project on DC-SCM 2.0. And he has invented a number of different interesting concepts to make DC-SCM 2.0 work better. He's been involved with DCMHS in that association also. It is just very good that we have 2 major OEM system suppliers, Dell and HPE, here on the stage. I'm from Google, so I'm a hyperscaler guy, and we have enterprise people here as well. All we're working together towards a common solution that we can take to production. So we go over a history of what DC-SCM has done, and then transition to hopefully what it can be. And we'll listen to you and whatever feedback you have for us. Perhaps the team members over here have done some good work as well Do we have anybody from IBM on open? So would you please join us? Yeah, yeah, yes, yeah,
We got an empty seat.
yeah. We have another seat. Yes, yes. This is another wonderful system look at the problem, and anyway. So Tim, do you want to send us through this? What is DC-SCM 2.0?
2.0 was, what we took was a couple companies that had thought through the scope of what they were trying to accomplish. We understood we weren't disrupting the world. We were wanting to evolve it. We were able to take, it expanded from those two companies to about 16 or 17. And taking everyone's feedback in, collaborating through spreadsheets and this kind of thing in real time of, well, what interfaces do you want and how are you going to use them? So you need to come to the table with an application of how you want to use this interface. And it's an interesting journey when you have lots of NDAs and lots of things, but you have to describe your applications of what you're trying to accomplish in ways to get the types of signaling you want. So it was a big Tetris game in the end of you had certain constraints of the types of interfaces you could put through there and overlaying them and having mutual exclusivity and dynamic reconfigurability. So, midway through the program, one new entrant came in and said, you really have a hardware co-design problem here that is not really dynamically discoverable and reconfigurable without walls of muxes, if you will, and switches and whatnot. So we really took it to, okay, we're going to, as well as multi-node came into the same play. In at the same time, two nodes on one HPM being managed by one. So, we took all that in, and now at the point we kind of finished the spec, there was a lot of mechanical cleanup, by the way, in terms of brackets and different wants and needs for usability, manufacturability, and robustness, that kind of thing. But we then started working on, well, how do we get the economic benefits of this where it's not a hardware co-design model? So we started what we called a DC-SCI Type 1 effort, where we have quite a few companies aligning on the different usages so that you have exactly one function per pin instead of 3 or 4, so that you can say, all right, well, type 1 is the scope includes a 1 to 4 socket server, single node. This is what it is. And it's been quite an interesting journey to get people's opinions to narrow and actually get agreement on what those interfaces are. Next step being the types of drawings you see on the screen here, and the true electrical interoperability aspect, so that the vision of I already have my HPM infrastructure, I just want to swap out the SCM, that's one camp, and then you have this other camp of I really want a journey toward drop-in HPMs that allow me to do take advantage of silicon diversity, and you're commoditizing the management interconnects and things that nobody really cares about. From a CPU vendor, someone who's creating a reference design may not be that interested in. So, a lot of the MHS stuff. And so it's been an interesting journey because MHS is going on at the same time and trying to figure out how to map use cases to how these interfaces are used and raise the least common denominator up as high as possible so that people will get all their check marks from their marketing at the end of the day for the products they're trying to accomplish. So.
And Todd, as you looked at DC-SCM 1.0 and your team dreamed up different use cases for it, you guys did something nice and interesting with that, right?
So Libre BMC, second, yeah. So first of all, from an IBM perspective, I've been trying to get our own internal teams to use the same cards and comment up on interfaces across our server line for like a decade, and really had no luck. And then we have this group, and we did a great job to get these defined interfaces, and then I was able to get them to buy in. It's like that was perfect, and I think that's going to be a good stepping stone going forward for all of us to have our servers be. They're cheaper. When you go generation to generation, you're able to just take a DC-SCM card and plug it into your new planer, and all those interfaces are the same. You can bring your system up faster. There's a lot of advantages here.
Right. So one major attribute of DC-SCM as being a module is that it has all of the special parts in one place that's not too big. It's a very small board. And the generic compute-centric elements are somewhere else. And those might be unique to a particular processor vendor. But the things that are customer-specific are on this module, on the DC-SCM module. So that makes it flexible for people to take risk. You don't like the BMC, you just change the BMC, you just test it out. If it works, you go with it. Root of trust might be different. CPLD might be different. So that the fact that it's smaller, you can play with it, was a success story.
Yeah, that's true. So then what we did on top of that is something called LibreBMC. So we still believe that there are security risks with using some of these ASICs out there. But if you had an FPGA instead of that ASIC that would boot your system, that would be, what we try to do is prove that that could in fact be done. And so just recently got it working. So there's, instead of the BMC, that's, the A-Speed AST2500 that is running on the DC-SCM, at least in our case, we replaced that with an Artix A7 FPGA and have all open code. So it's got an open power core, open power, or open everything on that FPGA, and it does in fact boot one of our big modern servers.
So what Todd is touching on is the fact that as part of the specification, as part of the base specification, the team defined the interface, DC-SCI, the Secure Control Interface. So on that, a lot of people provided feedback and eventually cast that one into specification. But then it seems that Todd's team looked at the module, the DC-SCM, the module, and said, well, I don't want to have a particular BMC that everybody else is using. I'll have my own version. And that version, in this case, was an FPGA. And hey, it worked, and the interface is the same. That team could innovate on that topic, and for the use case that they wanted. I have a picture of that. Maybe I should go there right now. This is the solution that you guys came up with, right?
Correct.
So you see on this particular board, there's a lot of green space. So they were able to consolidate some of the components that were discrete into one chip, and that chip is an FPGA. You know exactly what the code has been done. You feel comfortable about it being secure. So that came from the particular attributes of the initial definition of DC-SCM.
Yeah, and one of the main advantages of having an FPGA, again, is you can roll security patches out now into the field. If there was some vulnerability, a new vulnerability that occurred, you can just have a new firmware, a new gateware load essentially that goes out there, fixes that problem. So it's
right. So for this particular diagram, as you see, there is a BMC role on DC-SCM, but root of trust chip is there to protect the firmware that the system uses, the firmware that BMC uses. On the HPM itself, there is a CPLD that interfaces with the CPLD that's on the DC-SCM, and that CPLD's job is to basically abstract certain things that are CPU-centric. And wherever TPM goes, the Trusted Platform Module is a discussion point as well. Now, this is what was the past. So hopefully we can move on to the future, what could be, unless you guys have any comments.
Just one, since I've been in the industry, the DC-SCI interface has been the sticking point of 4 earlier attempts to standardize this sort of thing that all failed. So that's why we think, yes, there's still flexibility. Yes, you have multifunction pin capability in the overall if you're doing a kind of a hardware co-design kind of thing. But as we work through these SCI type design specs where you can target certain markets, we think that's kind of where one of these big benefits of why you see so many variations out on the floor and why we think this one's different than the previous.
Right. Okay, so on the first blush, we can see the type of devices that are on HPM can be consolidated. If we are working with CPU suppliers and say, okay, so we need some sort of a host, basically HPM manager. That device can be defined in such a way that the BMC on the DC-SCM can look into it and not necessarily care what type of CPUs you have in there. That's a concept, that we can maybe work together and define. That device could be a CPLD, it could be a small controller, it can combine the TPM and security elements on top of it. But it is a device, it could be a device to abstract different kinds of CPUs or even GPUs onto that module. Any comment there?
Early on, the HPM was defined as 100% stateless, and some people say, well, is it really stateless when you have those sorts of things? There's like an HPM FPGA, and our answer to that is it can start blank. You have a mutable attestation. You have all NIST update recovery. Yes, so ultimately it's not 100% stateless, but it is fully attestable. As still, the thing that's given you all that abstraction outside of the core value add of the HPM.
Right. So another abstraction can be done on the DC-SCM itself. So if we can imagine a device that does the role of BMC, combines all the GPIO and small logics that CPLD does, and maybe even includes the root of trust all into one device. Those devices probably are being built now, or we can challenge our BMC and root of trust partners, suppliers, to go consolidate. The starting point for DC-SCM was whatever motherboard component you had, put a block diagram around it, and take it out. Don't want to change anything because we didn't want to change software at all. Software guys didn't want us to perturb their work. That was the beginning of DC-SCM. But it should not be the end of DC-SCM. DC-SCM could really get consolidated, get smaller, and this is an example. Jean-Marie, perhaps you have some thoughts on that as well?
I got a couple of thoughts. Coming from the software stack, I think we probably need to add another module which is describing the hardware by itself. So that is currently missing, and this is something that we have on all HPE platform currently, like a EEPROM or even an NVRAM, which does contain the self-description of the system, which can be used by the software stack running on the DC-SCM module to self-discover the main characteristic of each HPM. So that might be easing the process of deploying DC-SCM modules on new HPM modules and improving the interoperability, and also really easing the life of the software developers. So I know that there is always a clear boundaries between hardware and software, but in the case of DC-SCM, we really need to bridge this gap or help each other to ease the integration of this software. So I think this could be directly integrated within this module. So instead of having CPLD, BMC, and root of trust, we might have to add some kind of flash or EEPROM for the description of the DC-SCM capability and the description of the of the HPM, because there is also some part of the DC-SCM modules which are optional, and that is something which is super interesting depending on the system configuration you want to deploy. But as this is optional, so we need to have a way at the software level to detect what is really implemented on the module without reading the spec.
Todd, is this the type of things that you guys have thought through when you were doing the FPGA design?
Not necessarily doing the FPGA design, but just thinking about the future as we've been looking at 2.0 and beyond. That you certainly have to have a way to detect what's on either side, and that is in the 2.0 standard, right? Demo, we've got the ability to see what's out there, and then what you'd want to do is either have a config file or probably a whole new image for your BMC, and also if you do an FPGA implementation, you could have an entirely different set of gateware as well, if you wanted to. Once you know what is on the other side, then you just program it, and it has all the flexibility you need. Then I think.
Yeah, my company, we've just reached about 50 platforms per generation and their general purpose configs. So you have this problem of moving toward a plug and play, self-describing I/O, the SCM knows what type it is at time 0. It can immutably discover and mutually authenticate with the HPM. Now you know the combination. That's not the end of the game. You have other things that mutate that to become your final model number, which you want very earlier in your boot sequence, so that you can configure device tree and all these sorts of things to understand your model specific. In the keynote, there was this, press for hardware-software co-design. And as we go through, how do you generate this to do this type of dynamic discovery? And how do you create the design maps? How do you verify that the hardware is what you wanted it to be architecturally? And then how do you automatically create the firmware, like device tree, setting up GPIOs or whatever kind of interfaces as an example? How do you do that? You automate the creation of the firmware. So these are the types of things that we focus on as we're trying to build out this problem statement of dynamic discovery and moving towards self-describing attributes and plug and play.
Very good. Again, the fact that we have done this, the fact that more than 25 companies, 30 companies now, are part of DC-SCM 2.0 demonstrates the value of this concept. And it has identified certain problems that we need to now work together. But now, because hardware is there, the software guys can get together and say, oh, okay, so this is specifically what I want, and the optimization can be done. So extending the concept of managing HPM to an add-in card, that's, you guys know, systems are not just HPM and DC-SCM. We have add-in boards. Add-in boards can extend to being an expansion chassis. People do that using a retimer card through cables to an external chassis altogether. But those things need to be managed, be secured, and the communication between the two entities need to be standard if we want them to be interoperable. So the concept of, if we extend the scale of DC-SCM out of just one HPM to multiple add-in boards and then to an extension chassis is a concept that we can think about as well. That could be done using some sort of a concept of a satellite controller. That's a, maybe we can call it a satellite management controller. That could be the same as the initial consolidated DC-SCM, or it could be a mini BMC. Those topics are being discussed within OCP forums. It's just a matter of providing enough feedback to that team to make it useful.
Yeah, there's a big effort right now in different standards forums, including PCI Express, of how do you do some of these control functions sideband, and how do you move those from low-level register manipulations up the stack to MCTP kind of transactions to do things that you need to do out of band even before, say, the ASIC comes out of reset, this kind of stuff. So when you talk about satellite management controller and everyone's desire to do attestation and root of trust for update and recovery and high-level protocol controls of functions like link subdivision, clocking, flexible I/O, all those sorts of things come into, yes, there's a bunch of efforts going on in those from a protocol perspective, but not really trying to nail down what the types of abstraction layer from a satellite management controller IC perspective that then fronts that into that what's shown as device, the major ASICs.
Right, and if we use already known and used and liked interfaces such as Redfish and PLDM and PCIe and all those standard mechanisms that are already there, it makes it easier for people to accept it, design to it, debug it, and qualify it for good use. Any comments?
Yeah, as Todd mentioned, our company are designing a lot of systems, from critical systems to industry standard machines. And the benefit of DC-SCM is huge because we can reuse the same modules. But in some cases, I got some pushback internally from very specific teams who requires high level of security for update protocols of firmwares like SPDM and PLDMs. And right now, this is not really standardized, and there is no clear software stack which is available on top of DC-SCM, which can be used to validate the compliance of each modules. And this will clearly enhance our adoption rate or improve our adoption rate within our different design if we could make it work sooner than later, and making it as a strong requirement within the next generation of the standard will be just great.
Yeah, I would second that. I mean, you can imagine a system that has many HPM boards, and it's heterogeneous, different vendors and different architectures, and you've got one DC-SCM card there that is then able to have a high-speed interface to all of those various HPMs and manage them all, and it would be the kind of the dream, I think, to get there.
The one caveat of that is there Nirvana single tenant or multi-tenant between each of those HPMs? Because it's a very different problem statement from duplicating interfaces and fan out to that level of isolation necessary if you have,
In the new world, you'd have to have multi-tenant, right? And you'd have to have that security and that isolation. And I don't know how to do it, but that's something coming for us.
There's just perhaps the reason I am interested in a lot of these concepts now is that I see CXL is enabling system capabilities that we didn't have before, or if we had them, we were not interested in building multi-node chassis with shared elements, pooled elements, and such in the past. But with CXL, we will have systems that have multiple nodes in the same chassis, perhaps, or even across different chassis using cables, and we need to manage them. We need to secure them. So the smaller footprint that we have for management entity, the more capable that entity is, the better we can scale. But to do that, I see that we should get together, dream up of the topologies of interest. How many nodes make sense to be in one chassis? How long of a link we could expect to have between chassis if there are expansion chassis, rack level or chassis level. Those type of things we should think through. And then perhaps another item before we leave, I would like to challenge the team is the out-of-band control is DC-SCM, and in-band control today is the SmartNIC. They have grown out of two different organizations within each company. They have different goals, but they have always been kind of related. There is an interconnect between the two. It's either an RJ45 or NCSI link. They need to know of each other and need to work together well. DC-SCM in the past was on the motherboard. The NIC was somewhere else. So you couldn't imagine for those to be combined. DC-SCM allows that modularity. And now if we go to a model that DC-SCM is just a chip, well, you can just think of that chip could be part of the SmartNIC itself. So you could have one entity that's smart enough to not only do the in-band, but also do the out-of-band control. That could be enabled by small devices, either in the form of satellite chips or central chips. These central chips could do CXL Fabric Manager concepts too. Chassis manager versus fabric manager versus baseboard manager or satellite manager. Each one of them is a different role, but perhaps one chip can be built to do all of them. That would be my challenge to the team. This is an example to say that if we consolidate a lot of components into one chip being in an ASIC or FPGA, it doesn't take much space. The space might be just the I/O connector in the back, and the rest of that could be much smaller.
Yeah, I think one of the challenges is to get this board size down. As we've been talking to people around the expo, it's too big, right?
Right.
As it is.
And some of the good work that the DC-SCM 2.0 team has done, Tim has been very much involved. LTPI is a high-speed interconnect with low pin count, and PESTI is another, this one wire, capable of running a lot of sideband signals. The combination of these multiplexing features can reduce the number of pins required. So you see the edge of the gold finger for this card is large because it started as being trying to do all of the GPIOs on that gold finger. But if we have a high-speed differential link between the two CPLDs in the system, you can reduce the size of that connector. Tim?
Yeah, or do more things in a multi-node world. If you can tunnel more things, you can theoretically tunnel eSPI and think, there's a lot of other stuff that we kind of took the easy road, commodity interface instead of architecturally in the first day, trying to do some unnatural things. You can see this is fixed length. There's a vertical form factor coming out very soon that pretty much had 2 lengths in terms of where it mates with the motherboard based on chassis depth. So this is the kind of thing that we're looking for feedback on, is if you wanted an internal only flavor of DC-SCM and how there's needs to cable from that or connectorize from that, as well as different types of submodules, mezzanines, attics on top of it. There's some very creative things I've seen at the show of people trying to triple the types of functionality in this sort of form factor. It's can be quite interesting.
We're coming to the end of the talk, but perhaps John will let us have a couple of questions. This is a panel of experts I have here with me. They can answer any of your questions.
Got two mics here for everyone. I think we covered a lot of new stuff, and they asked a lot of questions of the audience. I'm sure we got a couple responses we want to give them. Come on up.
Hello. Where do you draw the line between using a high-speed interface and probably using a wider interface to use simpler signaling versus more complex signaling to reduce the connector size?
Do you want to take it?
No.
You go ahead.
In fact, I don't know how to properly answer to that question, but what we observed when building our first DC-SCM 2.0 module is that there is this CPLD to CPLD interconnect, and we kept thinking about why don't we put more signals through that interconnect instead of having this wide connector. And I believe this is more an historical way of the way DC-SCM modules have been designed. So DC-SCM 1.0 has been designed in an intent to provide something which can be implemented, I wouldn't say in a quick and dirty way, but at least in a quick way. and then it has to move forward with some kind of compatibility in mind and mindset, and that's probably the main reason. But clearly, if we could end up into a situation where most of the signals could go through the CPLD to CPLD interconnect, that would be just great for our engineers, simplifying the complexity of the connectivity and probably saving a few cents on the connector side.
I give you my perspective or my historical background, DC-SCM 1.0, and then Tim can fix that with the 2.0. So with 1.0, no DC-SCM existed. So for the team to convince even peers, even engineers in the same group, to convince them that DC-SCM is a good idea, much less the managers, much less the guys that want to pay for these things, it was important for us to maintain software compatibility. We could not afford to do hardware in such a way that required firmware guys to do something new. So as we took all of the components from the motherboard and put it into a DC-SCM, we said, we're going to use the same parts, run the same software, and we just stretched the wires. We stretched the wires, and we had over 200 wires, and we couldn't fit them in that connector. So we came up with a multiplex scheme, the simplest way we could, serial shift registers, just serial GPIO, so that from the software point of view, there were still the same number of GPIOs, but in the hardware point of view, we multiplexed them on the connector. So that was the crudest thing we could do, the quickest thing we could do to get an entry into the world of DC-SCM. But then came DC-SCM 2.0, and Tim's team got there and made it better.
There's one GPIO on this 168-pin connector. We found that to be an incredible win compared to previous attempts. There's some no-brainer interfaces, PCIe, USB kinds of stuff. I've kind of bifurcated between real-time and non-real-time. If If it's a non-real-time function, BMC go offline, that kind of thing. Yeah, PCIe expansion, USB expansion, those things are pretty clear for a lot of management types of capabilities. The LTPI is really both. It's real-time, replacing serial GPIO, parallel GPIO, as well as non-real-time, remote UARTs, remote I2Cs, things of that nature. So there are a lot of things that we could do, and we've got some pretty good brainstorming here at this conference around tunneling other types of functions through there to be able to reduce that pin count, or to provide other functions within the pin count that's there, and go through a FlexIO negotiation of that kind of function. We also have our hands tied on some interfaces, like from the chipset, QSPI, TPM SPI, things of that nature, that it's like we're not going to put an interposer and try to tunnel that through an LTPI for security reasons, other stuff. You've seen Project Kirkland, you've seen all these kinds of things where they're trying to, you don't really want, there's already this sort of interposer threat, then to put more stuff in there to be able to hyper optimize that through some interface like that is, needs a lot of discussion.
And I just had one other thing that, there are there's a lot of different people and different use cases here. And so one of them is some people maybe don't even want a CPLD at all because for cost reasons. So now they're going to need that many signals and that width of that connector. It's something we have to deal with going forward. Are we going to force a CPLD or not?
Yeah, a lot of debates are on low barrier to entry. You want it easy. You want half of a person of doing CPLD work versus you can go hog wild when you move toward the plug and play mentality. And really, some of the stuff my company does is very bloated, I guess you could say, in terms of what you're tunneling through there, and extremely, but it's all around plug and play and dynamic discovery and this kind of stuff. So
Thank you, John, for giving us a little extra time. You see, that's an exciting topic to cover.
That is. Thank you very much.
All right, thank you.